I'll upload the recording later in case you want to refer back to anything. The slides are also available, like I shared the slides out, so I'll try to get them posted in the Spaces Slack and linked on the meetup page, but you can grab context from them. I'm going to briefly run through a little bit of a slide deck, and then we'll switch into actual Fusion 360 and go into things in more detail. There is one chair right up here if you want to get cuddly. Yeah, so what is this class? This is Intro to CAM/CNC, specifically talking about Fusion 360. So what is CNC? CNC is a terrible, really old acronym that stands for Computer Numeric Controlled. There are a lot of CNC machines out there. Mills, lathes, plasma cutters, water jets, laser cutters. If it's a robot and it's doing manufacturing, generally nowadays we call that a CNC machine. The C comes from the fact that before we had computer numeric controlled machines, we had numeric controlled machines that literally ran off punch tapes. Like they were still crazy robots that built things, but you programmed them either with like physical machined discs where the shape of the disc controlled how the machine would move, or with punch cards. So CNC machines were kind of a big innovation at the time, and were one of the first places where computers were like actively used and made people a lot of money. So CNC machines go back all the way to 1952, and like first ones were actually in production in the 60s, super dominant in the 70s and 80s, like drove a massive amount of manufacturing. These days, CNC machines are the expectation for how most things are being produced. The way of the traditional machinist has kind of passed, and probably 95% of all machined parts nowadays are made on some kind of CNC machine, or they're made on an ultra specialized machine for that. But programming these machines nowadays has evolved into its own specialty, its own crazy sequence of steps that you have to go through, and it's horrendously complicated, and I'm sorry. These machines are used by hobbyists at places like makerspaces, but the vast majority of CNC machine usage is in the industrial world with professionals doing it, which means that most of the tools that exist for programming and setting up these machines are geared towards professionals, which means they're horrendously complicated and take specialty knowledge to know and use. If you're ever looking for a good trade job, I think like a CNC programmer makes like $120K a year right now. If you know what you're doing, does not require a college degree, just requires having monkeyed around in some proprietary software for a long time. But the horrendously horrible flow that I have to teach everyone how to do is this three-step process where you have to design a part in some kind of software. That's what we call CAD, computer-aided design. Lots of softwares for that. Onshape, Blender, SolidWorks are common ones. I teach Onshape. That class was 2 weeks ago if you missed it. But you have to come up with a 3D model for your design in some kind of software. Then you're going to take that 3D model typically into another software that is a CAM software. CAM is computer-aided manufacturing. CAM softwares are the softwares that help you go from here is what my part should end up looking like into what the motions the robot should actually do to make that part. If you've worked with 3D printers before, 3D printers call this process slicing. And for 3D printers, it's really easy because there's just one tool and it's the nozzle, and even then they screw it up all the time. And the slicing is a challenge. But for a 3D printer, you still go through the step. You make the design for your part, you put it into the slicing software. The slicing software spits you out a file that you then take to the machine and actually run that file on the machine, which is the third part. And this, again, is yet another place where there's a bunch of different competing softwares and a bunch of different ways to do it. There are a lot of softwares that actually run on the CNC machines for interpreting that file that you hand to them, of which like PathPilot, Linux CNC, Mach 3 are all common and used everywhere, but every single CNC machine manufacturer has their own proprietary one that will come on the machine too. So you get into an entire world of hell. So when you try to do this professionally, you'll find dozens of softwares designing the upfront parts, dozens of softwares creating the intermediate G-code, and then that running on dozens of different machines at the end of the day, which has created a compatibility hell between all of this, which is annoying and part of what we fight today. The going from CAD software to CAM software portion has at least mostly been solved today. I would say the most common interchange format is the step file, which is good enough. STL files are used a lot, but they only approximate the geometry. But if you're having something like sculpted for like 3D printing, STLs are very common. And then there's a bunch of other formats. Almost all of the softwares can understand each other's different solid files to describe the shape of the part formats these days. After that, though, the output of the CAM program, when you've generated your toolpaths and I want to take a file from my CAM software over to the CNC machine, almost universally the format that is conveyed in is this thing called GCode. GCode is an abomination. GCode was designed before we knew what computer programming languages were and what good data formats were, and it is a mishmash of programming concepts from the 1970s that cause us hell still to this day. And because GCode is so bad, there is no standard version of GCode. Every single machine vendor has come up with their own slightly different syntax for what GCode actually works on that, which means that GCode is not generally universal. You can't really generate GCode for one machine and take it to a different machine and have it run correctly. What you'll find is there's this hell of post-processors where in whatever CAM software you're using, when you're done kind of laying out the operations that you want to do, you're going to click export, and you're going to pick, I'm exporting to a Haas, or I'm exporting to Linux CNC, or I'm exporting to a Tormach, and it'll add different flavors of GCode instructions to that for the different machines to understand. In general, the machines agree on about 70% of the instructions, and then for all of the weird bells and whistles, special functions that make our machines better than your machine, everybody does it in different custom ways, which gets really, really messy. Before we dive into actually talking about Fusion 360, we're going to go over a little bit of what the GCode actually looks like and how GCode works, so you have some idea of it when you end up having to debug this, because you will end up having to debug and you'll end up actually getting to the GCode layer. So GCode is a series of lines. Each line is one command. Each command starts with some command word and then some number of arguments after that. All of the commands are in the format some letter, some number following it. The first command that you should learn is G0. G0 stands for rapid motion, and it tells the machine to move to some location as fast as the machine would like, at what is referred to as the machine's rapid speed. So we don't care how long it takes it to get there. That's for kind of just moving around in free air. This command takes up to 6 positions following it, which can be X, Y, Z, A, B, C. If you had a full 6-axis CNC machine, which you can run GCode on robot arms. You probably shouldn't, but that is a thing that people do. Now, you might ask yourselves, where is X7, Y18? Nobody knows. It depends on like 9 other G-codes that are active on the system, because other G-codes set global variables that are in effect or not in effect at any given time. So what G0 does at any given time, you're not going to be certain of. The only thing that you're going to know is it's going to do a rapid motion in a straight line. I'm going to pause for questions. I just ranted for a while. No questions? Good. Okay. The other most common one, and both of these commands are really good to know, because when you get to the physical CNC machine and are actually working at it, all of these machines have literally a command line on them where you can type in G-code commands and hit enter and run them, and I will handwrite G1 and G0 commands all the time as I'm at the CNC machine operating it, just to drive it around quickly without me having to hold my finger down on the arrow key until it gets to where I want. So you do end up these are useful commands to actually know by heart. G1 is the other most common command. G1 does the exact same thing as G0, except it takes an optional argument for a feed rate. Depending on whether G21 or G20 is active at the time, the feed rate will either be in units of millimeters per minute or inches per minute. On our machines, you can pretty safely assume it will always be in inches per minute. But this command is now saying move from wherever you are to wherever this ending point is at this feed rate, which is how most machining operations on a machine will actually be accomplished. Now, with both of these commands, almost all the arguments are optional. If I don't specify a feed rate on a G1 command, it will use the most recent previous feed rate that was fed into any other command. If I do not feed it an X position, it will assume the same X position I'm currently at and say not change X. So you can just say G1, Y1, and it will move to Y1. You can also, and then this is buck wild, say Y2, and it will assume we're still in G1 and also move to Y2. You don't have to know all of this. There's just a lot of peculiarities of how these machines go. This is now where you can understand like the flavors of how GCode got a little buck wild down the line. They started adding all of these commands for describing arcs and different types of curves and Bezier curves and different kinds of special motion where you could get very complicated motions on the machine in a single line of G-code. Those were added to old machines because if you fed them a 1 gigabyte G-code file with every single little position for my curve, it would crash the memory on the machine. So they made fancy commands to overcome that, and all the machines support different versions of fancy commands, but generally G2 is very universal. And G2 describes a perfect circular motion for an arc, and you can feed in an end position and the center point of the arc, and it will arrive at that end position through a circular motion around that pivot point, and there is a clockwise, and I believe G3 is the counterclockwise version of that. Does that all vaguely make sense? Like, these G-codes exist, they're kind of a mess, but you can do things with them. Okay, we're going to spend a lot of time today talking about coordinate systems. By default, when you boot up a CNC machine, positions will be relative to G53. G53 is the default coordinate system in the machine that refers to positions relative to the machine's origin. Every single CNC machine will have that in a different place. And that is wherever on the CNC machine that machine decides 0 is. That's useless for us. We can't write G-code programs against G53 and have them work at all reliably on different machines. So the pretty much universal standard for how everyone writes G-code nowadays is using what's referred to as G54, or workpiece coordinates. So what we're going to do is we're going to place a coordinate system that we're going to call our G54 coordinate system somewhere in space that is usually attached to the piece of stock material that we're going to be cutting down. We're going to tell the machine where G54 is. We're then going to activate G54 on the machine, and then all of the coordinates that we feed into the machine are going to be relative to wherever that coordinate system is. Does that make sense? Okay, that is the single most important thing to get right when programming CNC machines. If you screw up G54, it is the #1 reason for horrendous crashes and broken tools. Because if my G54, I think, is defined at the bottom left corner of my part, but it's actually defined at the top left corner of my part, and I tell the machine G54 is at the top left corner of my part, it can cut all the way through my part to the bottom and be off by the entire thickness of my part because I got confused about whether I put G54 at the top corner or whether I put it at the bottom corner. So you have to get G54 right. Now, here's one of the great hells of CNC machining. There is no universal standard about where you should put G54 on your part. And there can be good reasons to put it in non-standard locations, particularly if I'm going to machine like one side of my part and then flip it over and then machine the other side. I might want to make the coordinate system for that second operation dependent on some feature I machined in the first operation so I can line them up correctly. What that means is every single program will have G54 at a different place on the workpiece that you're going to do. And you, as a machinist, have to load the block into the machine in the correct place, find where that G54 point is, and tell the machine that's where 0 is, and then it's going to do all of its cuts relative to that point. And if you screw that up, everything goes horribly wrong. So I beat the dead horse now, but that is how everything is done, and you have to remember that, and you have to get it right. The other thing that we're going to add while we're on this slide is, as far as I know, the mostly universal coordinate system orientation for CNC machines these days. And that is correctly depicted by this picture. If you stand in front of a CNC machine as you're standing at the operator doors, 99% of them in North America today will have the x-axis being positive to your right, the y-axis being positive away from you, and the z-axis being positive up. That matters because when we go into Fusion 360, if I'm going to lay my piece out with like the long side of my stock material pointed that way versus the long side of the stock material pointed this way, I have to set the orientation of G54 correctly in my CAM software as well. And however I want it on the machine, X is going to be to my right, Y is going to be away from me, and Z is going to be up. Does that make sense? Okay. This is what a very, very simple example GCode program actually looks like. This is a real program that you can go and run. You don't need to know all of these G-codes, but this is really just showing you some of the G-codes that exist and do different things for machines. T1 here is telling the machine to select tool 1 in the machine's tool index, which can cause different things to happen depending on what CNC machine you're using. It's pretty common for the CNC machines to track the length of the tool inside of the CNC machine itself, and for the machine to compensate for how long the tool it is, and for your CAM software to not know the length of the tool. So on the Tormach, our metal CNC machine, when I say T1, that sets the length of tool 1 for the length compensation that it's going to use. M6 is the command that M commands are kind of like machine control commands. That is execute a tool change. If the machine actually had an automatic tool changer, that would cause an automatic tool change to tool 1 to occur. There, good. G90 is, I believe, I actually am not 100% sure. I'm pretty sure that's setting up inches as the units for this program. G94, I believe, is setting up feed rates in inches per minute. I don't know. I Google G-codes all the time. You should Google G-codes all the time. You should make sure when you Google G-codes, you are Googling the G-codes for the machine you are standing in front of. Because yes, G90 on one machine will not always be G90 on another machine. I'm sorry. Welcome to hell. G54 is setting up, in this case, this is activating G54 and telling it that the current position is X0 and Y0. So where the machine is at the moment that line is being run is setting G54 to that. All of these subsequent commands are now going to be relative to G54. It's doing some rapid straight line motions. It's doing some feed rate motions here. I believe M3 here is turning on the spindle motor to make the spindle motor spin. I would Google that one as well. And then finally at the very end, M30 is into program. A lot of this changes, but that's the idea of what a G-code program can look like. Most of the G-code programs I run are somewhere in the neighborhood of like 20 to 30,000 lines of G-code that comes out. You don't want to write them by hand. You don't want to look at them by hand, but they are plain text ASCII files, and you can just open them and read through them, and sometimes that's really useful to spot strange mistakes or weird things or remind you what's going on. Questions there? Cool. Yeah, T commands are for changing tools. S commands change the spindle speed. G90 versus G91 switch you between absolute and relative mode. Yes, relative mode exists. No, you should not ever use it. Nobody uses it anymore. But in relative mode, if I ran G0X1, it would move 1 inch to the right. If I ran that same command again, it would move 1 more inch to the right, where every command is relative to the ending place of the previous command. Why anyone thought that was a good idea back in the day, I don't know, but it exists. There are some really good online emulators where you can type G-code into some simulated robots and watch them run if you care to learn how to write G-code by hand. I don't really encourage it anymore these days, but you'll get in there and play at some point. Everybody good? Okay. So you can write G-code by hand. You shouldn't. You should use some kind of CAM software. They're getting really good. I recommend and teach Fusion 360. The basics of what we'll learn in Fusion 360 today are universal to all the different CAM softwares. I do think Fusion 360 is the most powerful one that is the most freely available. There's education licenses for it and free trials and minimal versions of it that you can get access to. It is gobsmackingly better than most of the other completely free options that are out there at the moment, but there are a lot of them. When you get out into the professional world, like I think a license of Mastercam is like $20,000 these days. And there are reasons that companies pay through the nose for these, because if you're a professional machine shop, like good G-code can run a part like literally 20 times faster than bad G-code. The amount of value that you get out of a production CNC machine is driven a lot by how good the program for that machine is at making a given part. They care massively about like how fast can their people set up a part and how good will the machine run that part with that code. So like little optimizations they pay through the nose for. The last thing that you should really remember about G-code is that G-code controls all of the positions that are going to happen in the execution of the machine. Once the G-code file is generated, every position is fixed as to like what the sequence of motion that the machine is going to go through. While you're actually running that G-code program, you have some control on the machine to speed up or slow down the execution of the G-code, but you can't add extra motions on the fly or say like, oh wow, that's a heavy pass, I'm cutting too deep, I want to do another pass. You can't. You have to stop the program, you have to go back to your CAM software, you have to regenerate the G-code that includes an extra pass to do that operation in 2 passes. Get used to that. I will say, like, don't be naive in thinking you're going to generate a G-code file at home and bring a flash drive into the makerspace to run it on the machine. You need to be bringing a computer that is going to regenerate the G-code, because as you are learning, you're going to be regenerating that G-code a lot. Okay? Sweet. Fusion 360 time. This is what Fusion 360 looks like. Fusion 360, as you open it by default, will have a little panel over here with a bunch of different parts in it. These are all of the parts I've done in the past. Almost all of them are CNC operations. I do not use Fusion 360 for designing parts, although you absolutely can, and the people who use it for that tell me it's a pretty dang good software for that. I can't judge. I've never really tried. What I do whenever I open a part in Fusion 360, first off, my actual workflow is I do upload, and I upload a part that I grabbed from the actual program I designed the part in, which what I use for that is Onshape. So I will take my part, export it from Onshape, upload it here, and then it will open up in Fusion 360 just like this. And then I go over here to this top left corner where it says Design. Right now we're in design mode, and I come on down to Manufacture. And it's magically switched now from a CAD program to a CAM program. It is very nice that it can do both, but I only use it for CAM. So this is the basic layout of what Fusion 360 has. Along the top here, this bar is designed pretty well for you to do things correctly from left to right. It is trying to guide you correctly. The first things that we're going to do is control our setups over here. Then we're going to add a series of operations that are going to do things. We're then going to simulate those operations and actually export them to G-code. And then there's some functions over here for controlling our machine. And finally, at the end of the day, if we made a part and we wanted to like check that part, there's some options for inspecting the part. But you should generally remember the flow is going to be from left to right. As I start right now, Fusion 360 won't let me go ahead and do any kind of operation. Like if I try to do an operation, well, it auto-generated a setup for me. That's not what I wanted you to do. That's fine. This setups folder is empty at the moment. And the first thing that you're always going to want to do is to define a setup that you're going to use for a series of operations. What you should think of a setup as is as one clamping of this part into the machine. Every time you unclamp the part and change how the part is set in the machine, that's a different setup. For this part, which I have designed but have yet to manufacture, this is going to be a little aluminum cribbage board. And it's going to have this pocket in the back that fits a deck of cards and a pocket in here that fits the little pins. There's going to be magnets here so that it magnets to its matching half, and magnets here so that it magnets to the other half of the board and clips together to make a little backpacking cribbage board, which I think will be absolutely beautiful when I CNC it out of aluminum. But I think I designed this 9 months ago and haven't gotten around to actually running it yet. But for this part in the Tormach CNC machine here, this part is actually going to require at least 3 setups. I'm going to do one setup where the part is oriented like this in the machine, and I can come through and I can drill all these holes and engrave the top and chamfer the outside edges. I'm then going to have to flip this part over to do this, mill out this pocket in the bottom of it, and finally I'd have to do a third setup just to drill these holes in the end of it, if I wanted to do it. We're going to start, because I think it's a little simpler, with doing this pocket on the back side as kind of our initial operation. So I'm going to go over here, I'm going to click this button in the top left, which is the setup button. Also, good general tip to know about Fusion, if you hover over almost any button in it, it will pop up a big explanation of what that button is. So when I click that button, it pops up this little modal window that is for defining a given setup. One thing that I can do, yeah, I'll show it off for you guys. I almost never do this, but you can select a machine. It has a bunch of machines built into it. And if I select that, it'll pop, I think, a 3D model of the Tormach 440 into here. And it doesn't seem to actually do anything other than make a pretty picture at some points in it. But ignoring that, you can set up machines in it. I never do it, and I'm going to turn it off now because I think it makes the thing noisy. The first thing that you want to select in your setup is your operation type. And it has defaults in here for milling, which is what the Tormach and ShopBot here do. For turning, if you had a CNC lathe. For cutting, that you would use on a laser jet or water cutter. Water jet or laser cutter. And then additive. Yes, Fusion 360 can do 3D printers. I would never use it, but we're going to be doing a milling operation here. Now, the next thing that it wants us to do, and again, almost all of these menus are designed for you to go top to bottom, and then they have multiple tabs, and you go from left to right on the tabs. But now we're going to set up our work coordinate system, which is going to be where G54 is for this part. As I want to orient this in the machine, well, let's say this is the default. This is what Fusion 360 did right now, which would orient the part like that. Like the perspective we're standing at right now is how that part would be loaded into the Tormach if I was standing in front of the Tormach. The Tormach actually has a bigger x-axis travel than a y-axis travel, so I don't want the part oriented right like that. I want the part oriented like this. To do that, I have to pick this orientation tab. Right now it defaulted to the model orientation, which is whatever the orientation of the axes were as this thing was designed. I'm instead going to say select X and Y axes. I'm going to click somewhere on the thing, which is where I want the X axis to be. I'm going to click somewhere on the machine where I want the Y axis to be. And then I'm going to go over here and say flip Y axes because it made Z point in the wrong direction. So if I click flip Y axes, now that is X is to the right, Y is away from me. That is how I want it set up in the machine for this operation. The only problem now is I don't want to use that bottom point for it. Fusion 360's default selection mechanism is what it calls stock box points, which it basically assumes you're going to use one of these points on the corner of your piece. I almost always use either the top left back point or the top left near point. In this case, I'm going to use the top left back point. Why do I use that? On the Tormach, that's where the corner of the fixed jaw vise is, or the corner of the fixed jaw on the vise, which is a very repeatable point for me to be able to set the part up against, so I can take the part out and put it back in and have it aligned to that same spot. So that's what I tend to use as a same default. Your mileage may vary. But now I correctly have the coordinate system at the corner and orientation that I want. Does that all make sense?
Question, so like on a 3D printer, you got limit switches, so it automatically does something like the Tormach have limit switches where it automatically checks the set where your 00 is at?
Yes, so both the Tormach and the ShopBot have limit switches on them and go through a homing routine and set the machine's G53, the machine's 0, from its limit switches.
Okay.
Cool. Model right here, so if I had gone...
It's not visible.
What?
Not visible.
Oh, it's behind my head. Thank you, Shane. Shane gets a gold star. Oh, and of course, why did it make it bigger? Fusion 360, you're mean. There's a model option here for if I had in the design side of this designed like 9 parts, and I was actually only going to CNC one of them, you could select which of the 9 parts would be done there. Fixture can be very useful, which is you can actually bring in a 3D model of the vise that is holding this part and tell Fusion 360 what the vise is shaped like, and then Fusion 360 is smart enough to design toolpaths to dodge the vise. I've not done that a lot, but yeah, you can do that if you so care to. We're going to keep it relatively simple. So we made it through the first tab on the first window. Yay! Second tab. Here is where we set up the size of our stock. Fusion 360's default is to do a relative sized box, but here are all of the different ways that you can design your box. Almost always I'm using fixed sized box, and I'm taking a pair of calipers and I'm measuring my stock material and I'm rounding, so it's in the neighborhood. It is almost always advisable to overestimate the size of your stock in Fusion 360 rather than underestimating it. If you overestimate, it'll often start cutting in the air before it gets there. That's totally fine. If you underestimate it, it'll crash into it because it won't start cutting in time. And so it is better to be on the big side than on the small side, but that can have some weird side effects when we get into it. So I'm saying here is the fixed size box. I'm just using its whatever defaults it put in here. That's a big enough chunk of aluminum to get this part made out of it. Finally, you can go into post-process here. Machine work coordinate systems, well, here's a funny thing. You can actually have multiple G54s because GCode is evil, and G54.1 and G54.2 exist.
Oh, no.
Don't worry about those. Don't use it. Just know that's why that is there, and we don't want to mess around with it. And then lastly, this will be filled out for us when we go to generate this setup in a GCode file. We don't have to fill it out here. We'll be able to edit that in another menu. So I always ignore this post-process tab and never click into it, but I'm trying to be exhaustive in my explanations. So finally hitting OK now, we have a setup. Yay. Now we can start doing operations. So to talk about the operations that exist in Fusion 360, all of these are different operations that it knows how to do. And they are crazy. And they all have their own wild windows which control how they work. And they're all useful for some purpose or another in the world of CNC machining. There are so many of them. And they do so many different things. I use about 3 of them every time. And it's almost always the same 3. So I'm going to show you some of the basics. If you learn how to get through some of these windows with Fusion 360, you really can learn the other ones, but just know there's a lot of these, and they do all kinds of things. Like if you want to cut threads with a thread mill, there's a special operation for that. But the way that we're going to turn our part from just a block of aluminum to the final part is not one magic button where we say, okay, Fusion 360, go remove the material. We're going to tell Fusion 360 a series of operations that we want it to do to remove that material, and we have to kind of baby step it along the way with what algorithm to use for what circumstance. So the simplest operation is face. Face is what we do in a mill when we want to just make something flat. We're just going to run the bit back and forth over the whole top of the thing to make it flat. Almost all of my operations begin with a facing operation. That accounts for any kind of wonkiness in how I set that part in the machine and makes the thing flat to it. Now, we're about to get stymied for a nice long tangent, because the first thing now that we have to tell Fusion 360 when we want to set up any operation is what tool to use for that operation. If you made it for the Fundamentals of Machining class last week, there is a recording of that one posted. You learned all about speeds and feeds and why they matter and why they're different for different materials and how the combination of the material you're cutting and the tool that you're using determine the speeds and feeds. That's where all of this information is now used. So in Fusion 360, we go into Select, and it pops up this annoyingly ginormous window to actually select a tool. By default, you will have access to Fusion 360's library of all the default tools that it knows about. In this case, we're doing a milling operation, so I'm going into Fusion 360's library. I'm clicking Milling Tools. Here's all of the default milling tools that exist for Fusion 360. I would have to know what tools I actually have and what tools are available in the machine and what's in the library over there. And if one of those matched, I could go and I could say, okay, we have a 1/2-inch flat end mill. I want to use that. When I select that now, Fusion 360 populated this chunk of data down here with speeds and feeds for that machine for different types of materials that we might be cutting with that bit. So there is, wonderfully, an aluminum roughing set of speeds and feeds here. That should be mostly correct for that tool. And I would say in general they are. But Fusion 360 assumes you have a $250,000 CNC machine with it. So almost always these speeds and feeds are what would be right for a professional that is pushing a professional CNC machine to remove as much material as possible, and almost always they're too aggressive. So now you click the edit button, and Fusion 360, hello? Yes, okay. Oh, it's not going to let me edit any of them because that tool is read-only. So what we have to do is we have to copy this tool. We go into our documents library. We paste it into our documents library. We now have a copy of this tool that is a local copy, copied from their library, and now we can edit the cutting data for it. You're being extra slow tonight, Fusion 360. Okay, so the only real thing that I would turn down on this is the cutting feed rate on this. 100 inches per minute is just hogging material out. That is going to town. I typically on the Tormach don't run above like 30 inches per minute, particularly when it's a new operation that I don't quite know what I'm doing with. At 30 inches per minute, we're still above 1/1000th of an inch feed per tooth that it's calculating for me, which is what we said was kind of the right limit to stay above in the previous class, so that's plenty fine. Everything else will be totally fine about this operation, so I can now say accept. And that has the aluminum roughing edited for this, and now, oh, excuse me, Windows, select. Now we've selected that tool. When Fusion 360 did that, and I selected that tool, it pulled all of the feeds and speeds data from that tool's profile. That's really, really good and really, really useful for us because it means if I use that tool in a bunch of operations and I decide, wait a second, I don't want to run that tool that hard, I can go back and I can edit those settings on that tool and it will automatically update them in all the operations that are using that tool. That's really, really good. But I can also click right here and I can say 1100. Oh, dang it, I didn't mean to hit enter. Back. And it just accepts that. And it's now overridden that one setting for this one operation. And now when I go back to the tool table and I edit it for the tool, it'll update for all of the other operations, but not in the one space that I edited it. So one of the warnings I have about Fusion 360 right now is if you don't muck with settings, it will auto-update them for you a lot. Don't always trust those though. One subtle slip up of where you're clicking or like typing a number in wrong can get it different on one operation, and then if you go edit it on the tool, you can't be sure it changed on all the other places. There's 3 little dots here. If you expand these 3 little dots, you can normally there's a reset to tool default. Oh, I think if I click this equation. Nope, it got mad at me. Bad Fusion 360. I don't know. Oh. I'm going to say reset to user default. Okay, that time it figured it out. Why are you not showing me the actual numbers now? I'm scared. I'm going to ignore it. Normally those 3 buttons give you a way to reset it back to match to the tool, and I'm scared as to what's going on right now, but we're going to ignore that. Okay. The next tab, so first tab on all these operations will always be the tool. The next tab is always going to be picking some geometry for this operation to occur on. The only operation that I'm aware of where you actually don't need to set any geometry at all is the face operation. If I don't set anything for the face operation will default into facing the entire stock material. And it's smart enough to know that. So we get to ignore the geometry tab for this one, but we'll come back to it in a bit. The next tab is the heights tab, and oh boy, howdy are there a lot of heights. And they all mean slightly different things, and if you hover over them and Fusion 360 wants to bless you, it will explain what that height means. And this pop-up pops up with very tiny text that explains you what each of these heights will be used for. The clearance height, just to roughly explain, will be the height that it comes to with its rapid motion, where it assumes I am completely free at this point to move, I'm above the part, nothing's going to interfere with me, above the clearance height, Fusion 360 thinks it can do whatever it wants. The retract height is the height that it will come up to if it's doing some operation over here and then needs to traverse some space in between to come back down and do another operation. That will be the height it retracts to make sure it's clear of the part. Why is that different from the clearance height? I don't know. The feed height now is the height at which it will switch from rapid moves to actually having the spindle started and moving the tool and making sure the tool is cutting. So that's your little buffer region for you should definitely be cutting by now before you get to the top up. The top height is where it's actually now definitely cutting the material, and then the bottom height is where it's the lowest point that it will go to. These heights will exist for every single operation. On most operations, most of these heights won't get actually used for anything. For the face operation, the only thing that matters is the bottom height. It will face down to the bottom height every time. And by default, it did the right thing here, where it just defaulted to model top as the definition for defining where the bottom height is going to be. And it's saying, I am 0 inches offset from the top of your model. And it's now showing me here where all these heights are going to actually stack up to for this operation. That is what we want. We're through 3 of the tabs. Okay, passes is where you get to tell it if you want it to take multiple passes, and there are reasons for that, and step over and step down and direction, and multiple. We can check on multiple depths. We're not going to get into all of that right now because the face operation is really simple and it doesn't need it. The last tab is the linking tab, and the linking tab is for controlling how combinations of moves get synced together. You can imagine if I was going to drill 1,000 holes, and I wanted to control in the order of which it did those 1,000 holes, you have a lot of control over that with the linking tab. And if you were doing something like a water jet operation where I wanted to start cutting off of the edge and then come up to the edge, you can control where it leads in and leads out from and how it transitions into the cut. But none of that super matters for the facing operation. If I just hit OK now, it's still mad about all of this. We're going to go back to tool select. We're going to reselect our tool. We're going to reselect our aluminum default roughing. We're going to hit select again, and now it's magically going to have fixed everything down here that went wild. Don't ask me why. I hit OK now. It has now spat out what that facing operation is going to look like. These paths that it's showing are the paths that Fusion 360 has generated, and the different color codes on them mean different things. The yellow lines will be a rapid motion. This will be a slow motion. The green lines are arced motions. The blue lines are where it's actually cutting. We can now do a very cool thing, which is while I have this operation selected, I can go over to this button, Simulate with Machine. I can click it, and we can now watch it do the cuts. And I can slow down the speed and go back to the beginning, and we can watch it do that a little slower. And it'll actually show you how that cut evolves over time. Zippity-doo-dah, zippity-day. Nothing too wild, nothing too crazy. Questions there? We got through our first operation.
How deep do you go? How deep is it? Is it going to the 0 or a little more than 0?
In this case, it went all the way to the 0, I believe. We should double check that. In passes, there is this box for stock to leave, where if I checked, I could have left some axial stock if I wanted to come back and do a finishing pass. That would be the normal way you did that. That box was not checked. In that case, it faced all the way down to the exact surface of my model. Shane?
If the depth of the stock that you needed to clear on your face pass was thicker than the tool length, how would you specify the number of passes, or would it do it automatically? So say like instead of the amount you're taking off, it was an extra inch, and so the tool wasn't long enough to do it in a single pass at a single level and had to do 2 faces.
You're talking about if my part basically had a stair step in it and it was facing over here and then needed to come down and face over there?
No, like a single face on the top, but you have just a ton of stock material down.
Oh, so we want to do multiple passes.
Right.
Yes.
Would it automatically
No.
check that?
Passes, multiple depths, maximum step down. Let's say the maximum it can remove in one pass is 0.1 of an inch. now it generated 2 passes like that. You have to control that yourself. I'm going to cover that in more detail in our next operation, which is now a slightly harder one where we actually want to go in and we want to remove the interior of this pocket. And because there's a tight radius on this pocket, I have to use a smaller tool to actually get that tight radius. And I can't really shove like a 1/2 inch bit in there to remove all of that. We're going to do this in a slightly more complicated way and show off some more of the features with this operation. So the operation that I recommend you spend the most of your time getting used to is this wonderful, wonderful operation called 2D adaptive clearing. 2D adaptive clearing is the reason I use Fusion 360 instead of other CAM software. And the critical part here is this magical word adaptive. What adaptive does is Fusion 360 solves for a toolpath that has the most average consistent load on the bit that you're using. And that means it will figure out how to ramp into the material and ramp out of the material to not shock load the bit with sudden changes in direction where it just does like a right angle and does a right angle, and we're like part of the time the bit's cutting with half the thickness of the bit and part of the time the bit's cutting with the full thickness of the bit. 2D adaptive clearing is by far and away the most efficient way to remove the most material at the limits of a given tool, and is what I use as much as possible for my general operations. The only reason I wouldn't use 2D adaptive clearing for a facing operation is because the pattern that it does with facing makes it look really pretty and shiny. 2D adaptive clearing creates really wild, interesting surface finish patterns because it's doing this weird non-standard algorithm. Some people find those really attractive, some people find those annoying. I personally love them. So, for 2D adaptive clearing, right now it automatically defaulted to using the same tool from the previous operation because it knows tool changes suck. We want to do as many operations as possible with the same tool in so we don't have to mess with our tool. Now in our geometry operation, we do have to tell it what material we want to remove, and we're going to do that by selecting this pocket down here. I believe that's all that we're going to have to do. Yeah, we'll see if that works. For heights, it automatically set the bottom height to selected contour, and because I actually clicked on this bottom edge, actually at the bottom of where that thing is, that height is correct. I could click the right thing over here. It's going to be really hard to see that because it's opaque, but yeah, bottom height's correct. 4 passes here, I am going to, the most important thing to set is optimal load. So this is telling Fusion 360 how much radially I want my tool engaged while it's actually doing these passes. A good rule of thumb here is slightly less than half of the diameter of your tool, like around the radius of the tool, is a good starting point and will let you remove the most material with that tool. It is generally better to do a deeper cut where you're using more axial length of cut and less radial length of cut. You'll get more removal that way for reasons. But we're using a 1/2 inch bit, so 0.5, we're at 0.2, 0.2 out of 0.5, yeah, that's slightly less than the radius of the tool. That's a good point. Climb milling is the right same default, and so that you guys know, climb milling and conventional milling are the ways that the side of the bit is engaging with the material relative to the direction of rotation. In climb milling, the rotation is coming such that each tooth is starting on the edge and then sweeping through so that the tooth leaves on the side. Sorry, those. You know what? I'm gonna call an audible and just throw up a picture of this because I should have had it in my slides. Climb milling versus conventional images. Yeah. Climb milling, you're rotating like that while moving this way. Conventional milling, you're rotating like that while moving this way. Generally nowadays, climb milling is agreed to be universally better. You get better surface finishes, you remove more material. Back in the day, old school machinists swore by conventional milling because it put slightly less load on the machine and would like wear out your old Bridgeport less. Nowadays, everybody uses climb milling the vast majority of the time, and you can do both ways in some operations where it will mix the two together. We are going to do multiple depths, and we're going to do 0.125 to just not remove too much material. I'm going to check off stock to leave because I want it to go the full distance. And we're not going to worry about smoothing or feed optimization here. With linking, I think all of the default parameters will be right. The most important kind of interesting one in here that you might not have expected is this ramp helix thing. I'm going to tell you these default settings are correct enough for now, and we're just going to go ahead and hit OK and let it generate and see what it spits out. This is what it spit out. That might not have been what you were expecting, but it was what I was expecting. And if we select that and simulate it, we'll see what it's doing. Fusion 360 is smart enough to know that we were plunging a mill bit into a solid material where it needed to effectively drill a hole with that mill bit, and it's smart enough to automatically generate a helix. The majority of mill bits are not center cutting, which means if you use them as a drill bit, they won't remove any material in the center and they'll just fight and that material will back up and nothing will happen. So it's starting out here with doing a spiral. Why is it? Oh yeah, it's just, it decided to do a 0, don't ask me why. It's doing a pass where it's removing 0 material to start with. Normally it's smart enough to not do that. I'm gonna ignore that for the moment. Keep going. Now it's actually cutting. So just to, yeah, it spiraled down each time that it went down so that it didn't actually plunge the bit down at any point. That's all I'm really trying to say. That red part is it spiraling down into the next pass each time. Questions there?
If the center point is solid, how is it able to plunge down?
By going at an angle. And by going at an angle, I'm going to call a double audible and draw it on the whiteboard. If the center point is here and we've kind of got a bit like that, if we move at enough of an angle that way, this edge will always have caught where the center point ends up going into before the center point gets there.
Okay.
And so this is called your helix angle, is like how much of a ramp that is. Fusion 360's default for that is 2 degrees. And so it's moving on a 2-degree ramp, and that's enough to guarantee that this leading edge will have cleared before the center gets there.
Okay.
You can often use like 10-degree ramp angles for most bits and be completely fine. 2 degrees will work for anything out there and is a very safe way of doing it. But you see how Fusion 360 is generating these nice spiral patterns, yeah?
Yeah, I think this simulation is answering my question, but will the software stop you from, so if the mill is a half-inch bit, the smallest radius it can make is half an inch.
Yeah!
So it stops you from making the corners, right? If you have
Yep.
too tight of a, okay.
That's exactly right. So what he's pointing out right there is that the tool can't get closer into that corner than this half-inch bit could get. That's as tight to that corner, even though my model is actually that kind of weird line that's phasing in and out of existence as I zoom in. It did not get closer than that. And we're going to show that off in a second with our next operation. Other questions there?
So it knows what tool you, so if you had
Yes.
a smaller tool, it would take up that whole area.
Yes.
Got it.
And this is an important detail. Back in the day, CNC machines would do cutter radius compensation in the machine, and the machine would know the radius of the tool, and you would send it paths that were on the edge of where you wanted to cut, and the machine would offset those by the radius of the tool. Everybody gave up on that. Nobody does that anymore. That's not a thing that people do anymore, so all of your G-code is driving the center of the tool around, and Fusion 360 has to know the diameter of the tool and is generating the correct tool paths for that diameter of tool. So the machine will have a tool table in it, and the machine knows the length of the tool, and Fusion 360 knows the radius of the tool. Welcome to hell, but that's how it works. Yeah.
So we have 2 operations under one setup. So 2 operations under one tool.
Yep.
Is that order mean something?
It does, depending on what we do. So one thing that we can do right now is I could select this operation, and we're skipping ahead, but it's good to show it. If I click post-process right now, it's going to generate a G-code file just for that operation, because I selected that operation before hitting post-process. If I select this setup and then click post-process, it'll generate a G-code file for all of the operations in this setup in order in one G-code file. Fusion 360 for the free version, like the free version is very, very powerful, but tries to waste your time as much as possible. One of the things that the free version will refuse to do is generate a single G-code file with multiple tools in it. It forces you to generate them in separate G-code files. Fine, whatever.
Just depend, right?
Yeah, you just generate 3 files, you copy and paste them over. It does mean that you have to separately load each file and hit run each time. Doesn't matter because we don't have automatic tool changers. So you had to change the tool manually anyway. Doesn't hurt us, does hurt production shops. I think that's frankly brilliant software design on their part. Like they're taking away the features that you would need if you were a professional shop, but then giving us as much features as they possibly can to get us hooked on their software. Brilliant. Okay. The next operation that we're going to add now is going to add in the removal of the extra corners. You got it. I can't remember what the actual radius is. I think if I click here, are you going to tell me? Yeah, it's a 0.05 is what the radius I designed in my CAD model was there. That's evil of me. That's a horrible radius. Why did I do that? But we're going to make that happen. So we're going to do one more operation now that's also going to be a 2D adaptive clearing, although it probably doesn't need to be. I could probably get away with something else. We're going to select a different tool, and this time we're going to go through the manual tool creation window so you can go, you guys can see what it's like to create a tool from scratch. So we're now in my kind of document library for this thing. I'm going to hit plus. The first thing I have to do is pick the type of tool. I want to use a ball end mill because I had a really cute, beautiful radius in the corner of that. I want that radius in. So I'm going to select a ball end mill. First tab doesn't matter at all. That's just metadata to keep track of it. Second tab is where we define the geometry of this. I'm going to say this is a 2-flute carbide. The diameter is 0.05. It's showing me a preview here. The shaft diameter is defaulting the tool diameter. The overall length of the tool. Some of this matters in some circumstances. You can ask Fusion 360 to do a lot of things for you. One of the things you can ask it to do is you can actually add the full tool holder here, and it will model the reach of the tool holder and figure out if like the nose of the tool holder is going to hit part of your work as it's reaching into a deep pocket. No, those are features that exist. You're not going to get taught them tonight. Google them when it comes up. But if you care to access those features, you need to set up the length of your tool correctly. 1.5 inches, this thing would snap in a heartbeat. So let's say it's a 0.75, and hopefully that will, it's going to be mad about length below holder, 0.75. How much of it actually has a shoulder on it? We're going to say 0.6. It gets mad about all of these. Flute length 0.5. There. There's kind of what our tool looks like. And it gives, it shows you in the diagram here what each of these lengths matters for. Most of them don't matter that much, but you can set up a fairly complicated thing here. Shaft does not matter. This is for like crazy things where you're putting the tool on an extension to make a really long reach thing. If you were going to do some extra deep pocket on a machine, you're never going to do that here. Holder can matter. So we have TTS holders here for the Tormach. You can import the Tormach tool holder here. I can say this is going in a Tormach TTS ER20 collet holder, and it correctly pops in the model for that. That's what it would look like in the Tormach. So that's cool. That will get the collision geometry correct. Now we have to go into our cutting geometry, and this is where you have to know how to set all of these correctly to not snap this tool like a toothpick. Spindle speed for this one, we're cutting aluminum. We would like our surface speed feet per minute to be around 250 feet per minute. So we're probably going to run this thing near the upper limit of the RPM on the Tormach, which is going to be about 12,000 RPM. That still doesn't get us all the way up to the right surface speed per minute for cutting aluminum, but frankly, it's too bad because this tool is so tiny, you're just never going to get it to spin that fast.
When you buy like a bit or something, do you get like the speeds you should set things at and stuff? Or
Depends on how much money you pay.
Okay.
And most of those speeds and feeds are going to be wrong because they're going to be for very, very expensive CNC machines. But go watch the recording of the Fundamentals of Machining class that got posted. I cover the math to where you can actually sit down and calculate what these will be. I will tell you that I never do the math anymore. After you've spent some time with these tools, you've spent some time with these machines, you just get a feel for where the right windows for things are. You land roughly in the right window and you're good enough. The real professionals do the math to optimize every last bit out of it. Here you just need to be under things that are really gonna snap the tool like a toothpick. Feed per tooth is a little high for this tool, like 1/1000th of an inch is normally what we recommend, but this is a little tiny tool. So we're gonna be closer to 15 inches per minute as our feed rate, and we're gonna be at 1/2 of an inch, and I think we'll be okay. Ramp feed rate looks okay. Everything else looks good. Now, this is a really important part for this tool in particular, because this tool will snap like a toothpick if we don't take little tiny nibbles with it. So by saying use step down, this will default Fusion 360 to every iteration, every operation that we use this tool in, it will automatically do that operation in multiple passes. And this is as far down axially as we want to take a cut each time with this tool. The tool is 0.05. 0.04 is slightly less than the diameter of the tool. I'm gonna go half the diameter of the tool and say 0.025. That's gonna be a little tiny pass. Use step over. That would be more than the diameter of the tool. That's insane, Fusion 360. We're not gonna do that. We're also gonna say 0.025. So the maximum this tool will take as a cut by its default is 1/4 of the tool. It will take half the diameter in depth and half the diameter in radial. Flood coolant on, you should just always have. Post processor here, this actually does matter where we're setting the number of the tool. When the machine is tracking its tool table and is tracking the length of the tools, it will refer to the tools by number. We need whatever is on the machine and whatever is in Fusion 360 to agree with each other. Right now, it doesn't really matter because I'm not actually setting these up in the machine, but if I was going to run this job on the Tormach, I would need to go into the Tormach's tool table and make it match the tool numbers that Fusion 360 used, or if I'm smart, ahead of time, I figure out what is already in the Tormach's tool table, and I use those numbers here, and I say like, oh, this tool is already set up in the Tormach as tool 7, I'm gonna use tool 7. Make sense there? That's it, we did a custom tool. Yay, now we have a little tiny ball end mill. So, we're doing a 2D adaptive clearing. We're gonna select the exact same contour we selected last time, and we're gonna use one of Fusion 360's absolutely amazing superpowers that is horribly named. Rest machining. Would anyone like to guess what rest machining is? It's get the rest of it. You tell it, we already did an operation in this area using a tool that is this diameter, assume everywhere where that tool could have gotten to, and only get the remainder. It doesn't know that the previous operation exists. It knows nothing about the previous operation, but we tell it right here, I just came through cutting with a 1/2 inch cutter, and it knows how to do all the math. And that's it. That checkbox is miraculous, but also funky as all heck. Our heights are set up correctly. Our pass is automatically grabbed. Wait, we want to turn off stock to leave. So just know this, stock to leave is defaulted on by 2D adaptive clearing, where it assumes if you do an adaptive clearing, you're going to do a finishing pass. And it's like, oh, you wanted to leave a little extra stock. I never do. I don't like that.
On the table you just had before, there was a box for corner radius. Do you need to program that in?
Where was that?
Right there.
Specify the corner radius of the tool used previously to cut in the boundary. Yes, so if the tool that I had previously used was a ball end mill, I would tell it there the radius of the ball end mill that was used. In this case, the tool I used was a square end mill, so it doesn't have a corner radius.
Okay.
It's referring to the corner radius as projected. So 0 is correct. But if I had previously used a radiused tool, that's where I would fill it out there. Multiple depths, when I checked it, automatically turned on the step down we'd used before. Linking, we're not going to worry about at the moment, but I'm just going to hit OK and YOLO this, and hopefully it's generating a decent amount of material removal. But nope, it got it. Look at that. Look at that beautiful operation. It did almost exactly what we wanted, and if we simulate these two back to back, we'll kind of see what's going on here. This operation calls for a finishing pass because the handoff between the first adaptive and the rest machining will be slightly funky. I'm just going to speed that up until it gets coming in here. It's also, I didn't set up the feed height correctly. Here, what? You know what? We're gonna go fix that. You see how it's doing all these cuts in air? I don't want it to do cuts in air. I'm gonna fix that. The way I fix that is I go over here, I go to heights, I go to top height. It decided the top height was from the stock top, but I did a facing operation. I'm gonna say from model top because I faced down to the model. Now when that operation regenerates, it's gonna start cutting at the height I actually wanted, and it'll be less crazy. But just simulating this operation by itself, it's my laptop is chugging. It can't handle why it's literally lagging in the corners. Let me get it. Let me see it good. I want to see it good. Okay, slow down, nice and slow, nice and slow. We want to see this beautiful little corner getting stenciled out. Yeah, look at that. Look at that. Beautiful. And it did end up leaving just the littlest, you can see in the simulation here, there's just the littlest tiny wing that would be present there for whatever reason. Don't ask me why. Like Fusion 360, just not perfect. The way that we get rid of that wing is we add one more operation here, which was going to be a 2D contour. And 2D contour is when you literally just want Fusion 360 to follow an edge. It's using the ball end mill here. We're just going to select this bottom edge. We can ignore, I think, literally everything else we're not going to do in multiple passes. We're just going to say that, and we can simulate that operation. Oh, did it do stock to leave, you bastard? No, it didn't do stock to leave. Don't ask me why. But if we simulate this last operation, I am expecting it to come through, yeah, and just knock off those little wings that were left there. Zip. Just like that. Make sense? Questions? Cool. We could spend more time doing like the other pockets on this side. Actually, let's do these 4 holes, just because I think that's a pretty basic operation and shows off a little bit of what Fusion 360 can do. How are we doing on time? We got 20 minutes left. Drilling operation. We go and select our tool. We should select an actual drill tool. I'm gonna go, well, actually, before I do that, I'm gonna click on this. I'm gonna see what the hole diameter is. For some reason, I did 0.13 of an inch. I'm gonna pretend that's 1/8 of an inch. Drilling operation, select a tool. New tool, not new tool. Let's go to Fusion 360. And do they call them hole making tools? Yes, hole making tools is what it decided drills were called. And we can, I swear to God, there was, oh yeah, search here, 0.125. No data, 1/8. There we go. 118 split bit drill, there. Default drilling, I'm not gonna worry about it too much right now, probably good. Okay, there's our drill in. Geometry. There are some really cool methods for this. One of my favorites is diameter range, where you tell it, hey, find every hole in my model that is more than 0.1 and less than 0.2, and then it automatically selects all the right holes. That's so nice. That saves you so much time. Order by depth is useful if you have drill hole points at different depths in the thing. All of these are at the same depth, so it doesn't matter. Heights. This is one of the most important checkboxes, which drives me crazy and causes me so many annoyances where I have to chase stuff. By default, it will never remove material from your model that wasn't modeled in. So this hole ends right there. By default, it will take the tip of the drill bit to the bottom of the hole and leave that kind of corner wedge based off of the drill bit's angle there. Drill tip through bottom makes it actually drill through the bottom. Very, very useful checkbox to know, and it's hidden all the way down on this menu where you kind of have to scroll. So nice one to know. Cycles here, you can have it do, like if you're drilling really deep holes, you can have it do little go down, come up, peck, clear chips, break chips. Look at how many cycle types it has for different drilling patterns you could want it to do. Never use those. Drilling, wrap it out is what I always use. And just very quickly, we can simulate that with the machine. Zippity-doo-dah, zip, 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 zip. Good, nice, easy, sweet. Let's see, with the time we have left, I'm gonna show one more operation on the other side, and then we'll go through post-processing a little bit.
I was gonna ask on the very top, you got a fillet there. Is it possible to do that with any of the conventional bits, or do you gotta get like a router?
Yeah, there is a bit designed very specifically for that. If we click here, which is our tool library, so that just opens our tool library here, and I go into I'm gonna go into here, I'm gonna go into new, you'll see radius mill.
Okay.
It's a standard one. We have multiple here. I actually bought a radius mill just for this project because I wanted to get those chamfers ever so nice. You can also, though, like if you didn't have a radius mill, you could grab one of these 3D operations like morph maybe? I don't know which one would be the right one to use, but I could make that radius with a ball end mill and a bunch of passes. That would be slow as all heck, but you could do it. Make sense? Yep, sweet, okay. So flipping this over and wanting to engrave this text. The last one I'm gonna show is engraving because people like to engrave. We need to make a new setup quickly. By default, it will reuse the size of stock from the preceding setup, which is very, very useful. But I have to tell it what the new stock orientation is. So I'm gonna grab this stock point. Oh, that's not the orientation I want. What orientation do I want? I want the x-axis pointing that way. I want the y-axis pointed this way. It decided to change what corner there. X is to the right, Y is away from me. Yes, that is the orientation I want for this setup. Oh, and the Tormach appeared. Oh yeah, because I didn't unselect the Tormach. Yeah, so this is what this part looks like in perspective with the Tormach. Very nice. And now it's going to do a weird jumping around thing when we simulate, but whatever. There is a 2D operation specifically for engraving. It's pretty clever, it's pretty smart, it's worth using, and it's worth going in and grabbing a engrave/chamfer mill. I'm going to ignore all of the data about this tool and just assume all the default settings. You shouldn't actually do that, but we've gone through that a few times now. Geometry selection in Fusion 360, this one little window is probably the bane of your existence. This one little window can select contours, it can select chains, it can select pockets, it can select all kinds of things. When it's selected things, there's ways to edit the things that you've selected. So for instance, I'm gonna select like this outside edge here, and this is a closed chain 1. If I click it again, I can get to the chain editor. I can turn it into an open chain. I can decide how to propagate that chain partway around or not. There's a lot of controls in there. They're nightmarish. Know that you can do a lot to select individual parts of your model. In this case, we don't actually care about that because the engrave tool is really smart. And what we want to do is we want to grab the bottom contours of our letter. And unfortunately, I found no other way than to manually go through and click the bottom contour of every single one of your letter parts. And I'm sorry, it's a little bit of hell, but that's how you have to do it. We're not going to go click them all because that's fine. For some reason, it decided this is the correct bottom height. That seems buck wild to me. Oh, it decided the top height is here, and then it's going to go a 1/4 inch deeper than what I selected, is what it's deciding to do here. I'm assuming this 1/4 inch is coming from the engraving tool that I randomly picked and didn't think about the geometry of, and it's assuming I'm selecting the top contours of the text, not the bottom contours, because it's probably like, you generally wouldn't even emboss these into the actual surface. You would generally model these as sketches in Fusion 360, and we could just be selecting the sketch edges. We wouldn't have had to even make this geometry 3D, but I'm going to change this around. I'm going to say top height is going to be from the model top, and the bottom height is going to be the selected contours with no offset. That should be what I want. Passes I'm not going to worry about. None of that I'm going to worry about. We're going to let that generate. Sweet baby Jesus, what happened? Oh, I know what happened. Oh, that's wild. Let's just simulate that for the fun of it. We forgot to face this side. So it went straight into the, oh no, it's mad at me. Fusion? Okay. Oh, it's the stupid Tormach. It has to load the, yeah, so that's our engrave operation right now. That's not bad. It's fine. Watch how fast we can do a face operation. Face, select our existing half-inch flat end mill. Select. I know every other default's going to be correct. Generate the face. Good. Drag the face above the engrave. Yeah, look at that. And now we can simulate our engrave. But I am going to go into my setup and I am going to turn off the Tormach because it's just very annoying how much it makes extra lag when things happen. This is also one of the things that Fusion loves to do. It loves to generate these pop-up windows so big you can't get to the OK button on them. Yeah. Engrave, simulate with machine, and you can watch this come through. And it does these really nice little corner operations where it finds the corners of it and actually comes up and trims the corners into little fillets. And I think it frankly makes beautiful, beautiful, beautiful engravings. Although you can decide you don't like stylistically how they're made. There's other control options for those. But I like to give it these 3D things and have it engraved like this, and it gives it a lot of texture and a lot of pop. That's nice. Okay, time check, 10 minutes left. The last thing that we're going to talk about now is the actual post-processing. So just to demonstrate, this setup right here includes however many different tools. If I go to post-process and say I want to turn that into a file, it'll let me run through and spend a bunch of time on this menu and blah, 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 and then I'll click post. And then it'll say, oh, when you're using Fusion 360, you cannot post-process operations that contain tool changes. Just be warned there before you do it. We have to generate these as separate files, but I will select all of the operations that are being done in this setup. You can also see we're upside down right now for this setup, so let me just get us oriented right there. These are the two operations that we did with the big end mill. We'll generate those in one file. We'll go to post-process. When you go to post-process, you have to pick what post-process language flavor that you want to use. There are a bunch of these off the shelf available from Fusion 360's library. These are all of the different, slightly different G-code varieties that Fusion 360 knows how to talk. Yep. There's two that are relevant here, which are already imported from Fusion 360's library into mine. They are the Tormach Path Pilot, which is what the Tormach Metal CNC machine uses here, and Linux EMC. You don't want to use EMC2. EMC2 is available. EMC works better for our machine. You'll use EMC for the ShopBot. You'll use Tormach for the Tormach. I'm generating this for the Tormach. We're going to select the Tormach. When you select any one of these, it then generates a whole pile of post-process configuration settings that are machine specific. In case your machine has slightly different variants and different controls and you want to change slightly how the G-code is generated. Some of these matter a lot, like when you're generating for the ShopBot, you have to tell it that the ShopBot doesn't have a tool changer because it will otherwise generate tool change commands. And our ShopBot will reject those programs as invalid because it's like, I don't have a tool changer. I refuse to run this program. So there's like checkboxes over here for the ShopBot for turning off tool changes. For the Tormach, we don't actually care. The default settings work absolutely perfect on our Tormach at the moment. Really good advice to name your file. Really good advice to name your file with a version number because you are almost certainly going to be regenerating it multiple times. It is also very good to use descriptive names. I would call this half-inch face and clear. What is this game? What is it? Cribbage. Cribbage V1. That would be the name I would use. Document unit, you should always generate your G-code for our machines in inches. I also model in inches, so document unit is correct, but slightly safer to go ahead and specify inches there. And then I can say post. When I post, Fusion 360 takes these operations that it has, which aren't actually G-code right now. They're Fusion 360 toolpaths, and it turns them from Fusion 360 toolpaths into that flavor of G-code and spits the file out. It spits the file out in a slightly weird location, but you can find it because there's this really helpful button here, open output folder, and here's all the different programs that I've generated. So half-inch face and clear cribbage. We can open this file. Frankly, the best program that I've found for editing G-code is Visual Studio Code. This is what the G-code that actually got generated, it looks like. Fusion 360 is nice enough to generate it with comments in it, telling you what the file is, telling you what tool it expects to be using so that you actually know what tool should be used for that program. And then this is it. This is the whole G-code program. That's it. This is the end of the first operation. That's it lifting up. And then here's the start of the next operation, 2D adaptive. And it puts a little label in there telling me what that operation is. Blah, 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 blah. Down. Oh my God. Oh God. Oh God. Oh, sweet Jesus. Yeah. And then finally at the very end, M30 ends the program. I think like M5, M9 are like turning coolant off or something. That's what the G-code programs look like. That would have run absolutely fine on the Shopbot. Other things to mention in parting while we're still here. It is fairly easy with Fusion 360 to generate like 20 gigabyte G-code files. It will do things as precisely as you tell it to and generate absolutely ludicrous files. The files get fully loaded into RAM on both of the CNC machines we use. So if your file's over about 4 gigabytes, you're fucked. Sorry, sorry YouTube.
Demonetized.
Demonetized. The way that you fix that almost always is you pop open one of your operations. Let's pop open this 2D adaptive here. We glossed over this a few times, but in linking, I think, oh crap, where's this actual option? Oh no. Tolerance, right here. That tells Fusion 360 how tight it has to actually follow the exact geometry that is generated and can cause tens of thousands of extra lines of G-code to be generated. A lot of people come in here and they see 4 thousandths and they go, oh my God, no, that's going to screw up everything in my part. 99.9% of the time when it says when you say 4 thousandths of tolerance, the G-code that will generate it will actually be perfect. Fusion 360 won't round any corners that it doesn't have to round. If the paths that it's generating are straight lines and circular arcs, it will generate perfect straight lines and perfect circular arcs for those. Where the tolerance matters is if you have some crazy geometry that has some Bezier curve in it, and then it's trying to approximate some wild curve that you pulled in, then it has to approximate that curve as a bunch of straight lines, and that's where you get massive, massive, massive G-code files. So if you do pull in like a topo map of the US and try to like carve a topo map, you will want to be careful about what tolerance you have it generate at, or you'll get giant files. Generally right now, I bet I could take this tolerance up or down, and the G-code that we generated would not change at all, because I think Fusion 360 will have generated it out of common parts and follow the exact same path. So I don't expect any actual deviation in my part geometry from that being 0.004, and that comes down to what G-code commands Fusion 360 has available. I think I'm going to call it there. Yeah, we good? Sweet. I'm going to end the recording, and then we can just, I'll answer questions.